So I think this is good that is a closing talk because it's much lighter. It's more driven by visualization and looking at data and looking at how people can use maybe many of the techniques that have been discussed before, but more in terms of communicating with the users, in terms of understanding what's in the data. So not just in terms of who builds the algorithm, but how people that are not necessarily expert in topology, data analysis, and so on, and how they can look at the data and trying to understand what insight can emerge from that. So examples from chemical engineering, climate modeling, and things in that space. This is works that come out of the center that I lead in Utah. We have a variety of people working on data analysis, high-performance computing, and of course visualization. Again, all kind of techniques that come to play in visualizing data, especially in scientific domains, but not limited to that. And in particular, we're trying to understand from an analysis and visualization point of view what techniques kind of unify different domains. And in fact, definitely lots is borrowed from computational geometry and computational topology, but really the main aspects that we look at are work in kind of performance, understanding how to scale to large data, especially when you go to high dimensions. The data sets get larger and larger, data structures get larger and larger, and it's hard to work with them. That's very important. The analysis, in particular, how that combines with extracting features, present them kind of as an abstraction to the user so they can make sense out of the data. And I know that I'm going to use terms like structure in a very loose sense, but those are terms that are very meaningful to actual scientists in various fields, depending on the application domain they work on. And of course, user interface, usabilities, and I'll have a few examples of exploring high-dimensional data in interactive fashion. And I'll try to convince or convey that that's an effective way to provide more information. I've already seen a lot of work in doing the various persistent diagrams, barcodes, and so on. You can think of those as very simple visualization tools. This question of can we do more advanced stuff to help people go through the data and understand what the information collected really means. Very often being grounded on application domain is important because people at the end have to make an interpretation in terms of making a decision about, I don't know, how pollution is spreading, or do I have a certain amount of traffic that I have to change routes, or things like that. So, or say, build a kind of a new composition for a fuel to reduce pollution in combustion. So those are things that have to lead to an hypothesis, some way of deciding what to do and act on it. And so the quality of the information is very important. So here, the experience I'm drawing from is maybe in a couple of major areas. One is from classical scientific data. Climate modeling, it's a particularly important one. People build massive collection, run a lot of simulations, and then they have those ensembles of simulations, and they really get drowned in this amount of data, this in high dimension, large amount, and still have to decide what's going on. Is like global warming happening, to what degree, and things like that. And so there is a question of understanding, making prediction, calibrating models, making comparison between predictions and data from sensing or experiments, depending on the on different situations. Of course, there are many other more man-made phenomena that are equally interesting, especially for high-dimensional spaces. So communication networks, social relations, and so on. And what's interesting that I think many of those cases can be managed in a very similar fashion. So let's kind of look at the basic way of thinking of data. Especially for high-dimensional data, you have a collection, kind of a table or a database of a set of either samples of data acquired from experiments, or collecting from the environments, or built in many different ways. And so you have kind of your attributes. Some may be independent, like if you have domain and range in a function. But often, actually, when you explore data, those two dependent and independent variables can be exchanged depending on what you're focusing on, what type of relationship you're trying to understand. And of course, kind of your rows in the table are the kind of different acquisition. And by the way, some of the columns could be just the location. So point sets is a great example of that. You have the coordinates that the application person may associate with a particular meaning, but those are basically location in space, different dimensions. So we start from experience in lower dimension, and of course the intuition tells us that at least in 3D we're in good shape, right? So I look at something like this, I build in my mind a model, right? I see those figures, those are actually real satellites going around the Earth. I think of those going behind the Earth and coming back. I know what is the shape of the Earth and so on. So the reality is that we don't limit ourselves to look at the picture, at a visualization. We really continuously build a mental model. And depending on experience and prior knowledge, we may be confident that we build the correct model or not, and that confidence may be founded or not. But certainly in 3D we have a lot of experience. So here, kind of a very simple example. You have something like this, and then you start looking around in this painting, and oh, you notice that actually the hallway moves a little bit. So is this static or does it move? And here you can see even in relatively low dimensions, there is a total failure of intuition. I don't know how many at first sight were guessing that this was actually coming out. It was a static object and was coming out, and it had the illusion of a moving object that would go in. Totally the opposite. And again, we are in 3D. This is either a kind of more cute one. You have this, you go around and look at this object. The T-Rex keeps looking at you, and in fact the head turns, as you could swear that this object is not static. I can promise it is static. In fact, if you turn around a little bit more, this is the actual shape. Okay, and so this is a fixed object. And even after you know, if you look around, it's hard to not see this thing turning around. And then I've gone to the opposite side and now I realize how it is. Now, I mean, this is, and they call those illusions. There is no illusion there. It's a very simple shape, but the model we build in our brain while we look at this stuff is completely wrong. And this is even in static picture of 3D. So how bad it is when we go in high dimension, in light of a simple example like this, it's kind of a very interesting thing to think about. The upside is that here the illusion is created by the fact that we have a lot of experience, and in n dimensions we don't have a lot of experience. So we are a little bit more of a blank slate, and we might be wrong, but maybe for better reasons. But generally, just looking at picture and moving around is not so efficient. So we looked a lot, even for simple 3D models, how to use technology like topology, and kind of my fixation has been in use of Morse theory, to turn the data into kind of different type of structures, so that you don't just look at raw data and spend a lot of time into that, but you actually can turn a model made of voxels, very high resolution, into, say, simple line networks and things like that. So that's closely related to some of the Delaunay triangulation that we saw before. And that has been very effective in a number of scientific simulations. And to some degree, it's one of the bases that we're using to say, okay, if I want to look at data with a certain complexity, showing explicitly those models with topology and connectivity in different fashion tend to be very useful in practice. So when we go back to the basic idea of showing high-dimensional data, kind of what are techniques that are being used in a way used in very effective way, and why we might need to do better, how good they are, and how they fail. I'm not going to do a full overview, but just a couple of examples. They give a sense of things that have been very successful. I mean, people do all the time scatter plots. So scatter plots basically pick two of the dimensions out of your set of n possible dimensions. You effectively project all the data in that subspace. And then, for example, on the left, you see the typical matrix you get with all possible scatter plots. In this case, it's 2, 4, 6, 8 dimension give to 64 possible scatter plots. You see how that's a quadratic form in terms of the number of dimensions. And beyond the number, right? I mean, if you're a person like me that want to make a visualization tool, as those scatter plots increase in number, they become smaller in terms of the space I can use in my screen. So that's clearly a type of technique that does not scale. At the same time, you see many are kind of similar to each other, so I really don't need to show all of them. So they have been working developing metrics. You see the rows there show with different colors the effectiveness of each of those metrics that you see mentioned in each row, so that I can select a subset of those plots that are particularly meaningful. The reason why this is successful is that the dimensions are understood. I can show a user, oh, this is pressure versus temperature. They know exactly what it is, and in fact, they know better than I do. And so they can make sense of the data, but they cannot look around as much as one would like to build them a good mental model of the object. But remember the metrics, I'll use it later. It's important to be able to look at a visualization like a simple scatter plot and somehow decide, oh, if all the points are kind of randomly spread, probably that doesn't tell me much. If they have some cutoff pattern and structure, and so here some are called skinny or different way of understanding the distribution of those points. Those are indicators that can tell you probably a user can spot something there, some relationship, some pattern that could be useful. Some of you could be useful also to be familiar with the concept of parallel coordinates. This is another technique that it's interesting but has different scaling problems. So here the dimensions actually are, that's why they call it parallel coordinates. The axis of your space are parallel lines, and on every point in your space is actually a line connecting its coordinates in this plot. And so two major, I would say, potential pitfalls are the fact that you can reorder those axes and you get a very different picture. Maybe that's an exploration feature, but it's certainly a challenge. So those two are actually the same data set, although you see very different perspective. But you could think of this as you rotate an object, you see different views, and you build a model behind the object itself. The bigger problem in scaling before was the number of views. Here, the number of dimension is fixed, but every point it's a line. So as I grow my sampling of the space, which is supposedly a good thing, I end up having a more and more entangled mess of lines, and I start losing any notion of patterns. By the way, I mean, those are now meant to be general criticisms. Those are actually techniques that have been used a lot, and I'm sure they will be more and more used in the future. Another direction is often to actually build specialized interfaces. This is actually a very effective interface to show the network traffic on a supercomputer and the use of the cores on that machine. So if you're familiar with a particular, it's called the Dragonfly network, this is extremely useful, interesting. You select things and so on. Of course, if you're in the business of building general tools, this is not very effective. You really have to know in advance what people are looking at, and the lines inside the circle are really physical cables out of a machine that do a connection, and the color tells you how much traffic goes on the cable. That does not map to easily another domain. And so we have done things like this in multiple situations, but it's one of those things that you try to maybe learn something about, but in some sense get away from, just because every time you will have to learn about the new domain and build effectively a specialized tool. So if I go back to my table and the fact that I like topology, one way of looking at this is say, okay, I'll take a bunch of my columns and I call that my domain X. And then I look at one particular value, one particular column. I call it a figure of merit, and that's my value on that domain. This is actually something that makes very easy to say, okay, for a new application space, I simply have to make that decision. And I probably do it multiple times. What are the columns that I consider the domain, the manifold of my space, if you will, and what are the values that tells me if things are kind of good or bad. If high values have a good meaning, like, I don't know, temperature in a combustion could be, is expected to be high. If it's low, things are not burning. Or if I'm talking about pressure in a climate simulation, we found that that's often how people look at the data. And so it's a good, somewhat generic pattern that one can kind of build tools around and in some sense recycle the techniques and so on. So under this, then one can take the more classical approach. Okay, I'm just analyzing a function on some domain. So here I pull my hammer, so this looks like a nail. So I look at a function. I have a nice intuitive model that, okay, even if I work in high dimension, I can tell a user, well, think about you have a terrain and you're looking at valleys and hills and things with high values that somehow you think are good. Those are your hills in the terrain. So it makes it easy to build a mental model, even if you are in a space that are very unfamiliar with. And so here we can build also a nice decomposition of the space. I assume most of you are familiar with Morse complex and Morse made complex, but effectively the Morse complex is kind of an equivalent of a Voronoi diagram. Here you have the maxima at the center of the cells and then the region nearby. First you can do it for maxima or minima, or you can do the Morse made complex in crystals that connect the maxima and minima. So in general, give you a canonical decomposition of the space that can help you drive your exploration and has not used yet any information about the specific domain. It's just a function on that domain. So, and with this simple type of model, for example, we can jump in and start analyzing something like here. We have a simulation. This is done at Argonne National Lab. We also have some collaborators at Livermore doing a similar application where we're taking this atomistic simulation of this lithium-ion battery. Now we're still now in 3D, we're not high dimensional yet, but you see how I can go from the raw data. The visualization could be more or less misleading. The network of lines you see there, those are the lines coming on the Morse made complex. And those actually follow exactly the location of the atoms. Particularly here, they're looking at those cycles. If they are hexagons, they means actually the charges remain well stored in the battery. If you have those exceptions with cycles, they have 7 or more sides, and that's where actually the charge leaks and your battery will not last. But more importantly, we build the whole system without knowing exactly what type of data it is, and the scientists make an interpretation over the data. We just give the key of understanding how we work with the data. Now, as seen also in the previous talks, this information itself, even if simplifies a lot, can be overwhelming. So you want to build hierarchies on top of the data sets. So here you can do contraction of critical points. There are simple rules about you can contract critical points of indices that differ by 1. In 2D, that means that if I have a saddle point and a local maximum, I can contract, and from the bottom left, I go to the structure of the bottom right that has fewer critical points and one fewer hill. And that can be done entirely combinatorially, so I can have a data structure get simpler and simpler so that it does not kind of make the user overwhelmed all the time with all the details. On the top, you have a way also of taking that type of model, kind of squishing it down to a representation we call the topological spine. Effectively, kind of, even if you're in high dimension, you just take those graphs of maximum and saddle points of index n-1, and you can lay them down on a plane, again, so make it easy to visualize and understand. So there you can say, take a simulation like the one on the right, that's effectively a 2D simulation. You have all the critical points at fine scale, but then you can show the structure at the coarse level that you see on the bottom right, or you can take a terrain and show it as a simple graph, however you like. And then when you go to real data, here it is a porous material. Again, now we're still in low dimension, but you see now I can do my topology in a hierarchical fashion, and so I can show a scientist that graph. Effectively, I can throw away my raw data altogether. That typically gives me 2 or maybe 3 orders of magnitude, depending on the data, and I can explore the structure of this porous material. In fact, the structure is more similar to the way a scientist think about the porous material. They don't think about all the atoms, they think about those lines. And this is already kind of have the lines in vector format and so on. So can we take advantage of this type of way of looking at the data and use it to visualize high-dimensional data in an effective way? And of course, the answer is yes. What we do is we look at the high-dimensional data sets, again, as a particular function on a domain, given the proper approximation of using a kind of neighborhood graph for the connectivity of the domain itself. And then you can think about, in this case, actually, this data set has 20 dimensions. The graph you see is the topology graph. Red, so red is high value, so you have 2 hills and 1 broad valley around it. And then the halo you see around, those are kind of you can think of that as the standard deviation of the distribution of points around those hills. So you get an intuition of how large they are. How this compare to classical way of looking at the data. So on the left you have those are 2 views of the same data sets. On the left you have just the points projected on the 2D space, and the other is the topology projected. You can spot the fact that they both have 3 minima, but on the left one I really have to highlight them explicitly, otherwise I wouldn't see them. On the other, the lines highlight that kind of in a natural fashion. And this has the big advantage that effectively the complexity of my visualization is driven really by how many features I have in the data, not by how many points. So increasing the number of points does not create clutter in the data. And then I understand even better how things are related to each other, the maximum and the minima. Even if you see in the display, the 2 minima on the left are kind of overlapping, you still can tell the difference. So this is kind of the key for looking at a visualization of this type. This is for a 10-dimensional visualization. You also have a nice partitioning of the space in separate subdomains so that I can actually study them independently. So I can reparameterize my data along the topological structures. So those are crystal, they naturally are monotonic from a minimum to a maximum. So I can build 1-dimensional plots on the right where the x-axis is actually the line that connects a minimum to a maximum. So here you can see the various quantity in this particular data set, the samples, and so you have this natural 10-dimensional view, and then the one-dimensional plots of each of those quantities with the structure that interpolates them. Obviously, I can use standard visualization approaches like parallel coordinates or scatter plots to do a further investigation of the data. So there is really a notion of really interplay and working together to look at this type of visualization and understand how the data evolves. So here, this particular kind of little study on a combustion simulation. Here we have 10 different chemical species where scientists want to understand how to blend those to build a fuel that does cleaner combustion. They're looking at high temperature as a good figure of merit. And so here you see the 3 minima are the condition that you want to avoid, right? The condition where the temperature is low, things are not burning. So for that particular crystal, you actually have a condition of pure fuel, non-oxidizer. So that's actually unremarkable. It's obvious for a scientist how to deal with that. Here you have the complementary condition, oxidizer, no fuel, still unremarkable. There is this additional minimum that is actually seriously problematic. Here you have a fuel that has the right composition, but it does not burn well. And this is the condition where you have those extinction reignition condition where basically the fumes of the combustion extinguish the flames temporarily. And that's where you want to stay away from. So kind of here there is a mix of good news, bad news. The bad news is that those conditions that were suspected actually do exist. The good news is actually that they had no idea in the whole space whether you could have hundreds of different ways of doing this, and it seems fairly localized. So you could think of, you want to be in the top plateau of near the red part, and just you want to make sure you don't drift in that particular direction. The others are trivial to deal with. But again, help, more important to the scientists to kind of map out of those complex simulations how those different conditions relate to each other. And this kind of a simple navigation through the data was kind of one of the early approaches, and see here how we navigate through individual crystals to show how the different quantities relate to each other. Another example is kind of 20 dimensions, same key for understanding the data. So here we have actually those two maxima that are different, what they call global long wave flux. So those are conditions of rotational movement in the atmosphere. So think of tornado or hurricanes. That with classical statistical method, they could not separate. They kind of had an intuition that they could be different. And so in this interaction with the data, they can actually see how the coarse model that had one maximum and one minimum, and there was the maximum, the more detailed analysis they could do. Actually now he is separating, and this CMF tau and tau variables are kind of in opposite relationship with each other, and they create those distinguished conditional rotation that before, without this type of segmentation, couldn't analyze much worse. They couldn't build an interesting model around. And the last example is actually for a nuclear engineering application, where here is this 6-dimensional model is kind of the simplest model, the realistic model of a nuclear reactor. And so here those red high value conditions are all bad. On nuclear reactor, you don't want to have the temperature go too high, it goes to melt down. And now the question is, when the temperature goes up, do I have to shut down my entire nuclear reactor, or can I understand in what condition I am so that I can make an intervention that is much more targeted? With this topological segmentation, clearly there are 6 distinguished conditions, and the problem is, can I tell which is which? It turns out that after segmenting the data in those subdomains through the crystal and reparameterize that you see on the right, there is this variable, the pump trip pressure, that suddenly those 6 fingers in the data are nicely separated and parallel to each other. So after this reparameterization, one can visualize and detect a particular condition just with a single variable. And that was kind of not possible to do before, with no kind of level of understanding uncertainty. And here can help kind of make an important decision on something as important as driving a nuclear reactor. Now, in general, I mean, implicitly here, I've been throwing a bunch of visualizations into the data. But there is the important question of kind of what's the best way to look at the data. I mean, high dimension, I can do some analysis. How do I look at the data, and how do I make sure that in some sense, I believe what I'm seeing? Here there are cases where what you could do is to actually take your data, parameterize it, and in some sense unroll it. So this is a simple case in 3D where your data set has kind of this spiral structure. Any kind of linear projection would overlap. And so one has to make a decision of, do I want to go to a place like that, where like in the right, I just unroll the data and look at that way? Do I look at like more on the left and in a classical linear projection? What are the upside and the downside? And in some sense, we have been looking at this kind of as a trade-off of complexity of the visualization and kind of easy of interpretation, right? So if I totally reparameterize the data, I'm in a space that is, I mean, unless I control fully the parameterization, I have really no idea how I'm looking at the data. If I do things like linear projection, there is a more, given the experience in 3D, there is more intuition of what's going on. And of course, if I go down to axis-aligned projection, the scatter plots that we saw at the beginning, that's in some sense very intuitive, but very limiting the way things you could do. So in this case, we have been looking at trying to use linear projections in a more systematic way without going as far as to the nonlinear case, although that's something that obviously it's interesting to do, but increases the complexity in a very substantial way. The question is, what is the information loss, right? If I take a linear projection from n dimension to 2D, right, that's a linear map, and the kernel of that map has basically n minus 2 dimensions. So every point from in my picture represents an entire n minus 2 dimensional space. That it's already a massive, in some sense, loss of information that we have to make up with, maybe through representation of structure or through navigation in the data. And that was kind of what you were seeing already in the previous example. The 3D case, it's a little bit misleading because it's a special lucky case. So since we go from 3D to 2D, the kernel happens to have one dimension. And now in that kernel, you can actually define an order on the data that makes sense. In 2D, you can order points. And that's why you can say what's in front and what's behind, right? But I remember that when we first look at the high dimensional data, we're thinking, oh, I'm in dimension. I think of this hypersphere and navigate as in some sense you can parameterize your viewpoints on a sphere in 3D. That does not work anymore. It's more interesting in a way, but definitely more complicated. So this is kind of just to give an idea. If I'm projecting from 2D to 1D, like in the top side, right, I could parameterize all my viewpoints just on a circle. If I'm looking at things from 3D to 2D, I can parameterize things from all the direction on a sphere, modulo actually the opposite direction if you don't order things are actually identify with each other. So what does it look like if I look at all possible projection from ND to 2D? Think about, we can do all the scatter plots. I have n squared of those. I can have various linear discriminated analysis. This is when you want to separate clusters. Obviously PCA. So there is a number of things. When you explore all this, what is the dimension of this space. Again, not the space itself, but the space of the views into my data. And so, fortunately, this is actually a well-studied manifold. It's called the Grassmannian. And so there is a manifold where every point corresponds to a view that maps my n-dimensional data to my points on the screen. And of course, you want to, so when I kind of change viewpoint, effectively I'm navigating in that Grassmannian implicitly. And in terms of what views are distinct from each other, if I take, for example, a scatter plot and I simply rotate on the screen, that's understood as being the same view. It's at the same point on the Grassmannian. So those are really the distinctive, the views that are effectively different from each other. The bad news is that the dimension of this actually grows twice as fast as our original space. So if my data set is dimension n, the Grassmannian has dimension 2n minus 4. So the famous cursed dimensionality actually get worse. But effectively, when I'm visualizing the data, kind of that's what I'm doing. So yeah, at least in terms of understanding the space I'm working on, there's kind of no way around it. So in 2D, so if I'm looking at 2D picture of a 2D object, since we consider equivalent to each other rotations and translation, there is really just one valid view, has 0 dimensions. When I go to 3D, in fact, it already jumps to 2 dimensions. Of course, when you go to R4, now you're instead, in fact, 2D is the surface of a sphere, more or less. So when you go to 4 dimensions, the view space is already 4-dimensional and keeps going. So it's interesting, but more even higher dimensional object than one has to deal with explicitly. So when I go to n dimensions, so the dimension of my space is 2n minus 4. And so you have lots of views that I have to choose from. So the ideas that were originally from maybe choosing scatter plots become even more important and interesting. Out of this sea of possible views, how do I pick good ones? And certainly I cannot just give a tool to a user to explore implicitly this high-dimensional space because he wants to already explore a high-dimensional space and kind of lost with all the knobs in the tool itself. But also in terms of what people will understand, right? This is the typical conundrum when you have an object and at the end you look at kind of different views. It's easy to look at different views independently, and each view might give you a totally different understanding of the data. So I don't know if you're familiar with this. You have the blind man touching an elephant, right? If you touch one of say if you touch the trunk, it might feel like a snake. The tusk might feel like a weapon, and so the skin feels really hard and so on. And in a way, it's kind of mentally, you are kind of the blind guy stumbling in this high-dimensional space, having a very biased local impression about the data. Can you actually build a mental model that is conducive of the actual object itself? Right? How can you avoid being misled, or in some sense mislead yourself, since you set up the visualization and so on? So let's look at how things work. Again, going back to 3D, that is kind of very simple. So if I have a couple of planes and I just sample them with points, and in this case, if I do a PCA projection, I get effectively those two lines. And you see that, yeah, that spread my points. I bet you look at those two lines, you think of 2 lines, you don't think about 2 planes, right? So clearly you need more views. And so, but if I select the points in one of the plane, I actually spread that and I do PCA of that. And so in some sense, this is what you would think in terms of subspace projection. And if I take the other plane, I spread the points. So now I have 3 views that actually, if I coordinate them and understand them properly, give me the picture of how the data look like. So generally, we're thinking, okay, in the space of view, I want to start sample, in this case, just with those 3 views, and think of them as a graph that cover, or if I want to think of that as a more as a manifold, but that covers that space of view itself, so that I think of navigating through those views, right? Here I have my PCA, the first plane and the second plane, and if I quote unquote rotate from one to the other, I go from this view to this view, and so here I can start doing the actual rotation one way, and then I can do rotation the other way. And the fact that I can interpolate through the view, it's very powerful. Not the three views separated, it might make it hard to understand what's going on. The fact that you navigate is essential to build the overall picture. So let's look at this. For example, if I start looking at some high-dimensional data, this is data sets. There is a set of images of a number of people under different lighting conditions. And so those can be clustered depending on people. So we look at clustering that automatically. There is some ground truth. Can we explore this space and understand, say, whether the clustering algorithm behave well with respect to the ground truth, and work on that. Those are over 400 faces, and basically the dimension of the space we work with, it's 100, so basically reducing those pictures to a very, very low resolution and using the value of those basically as the vector representing each image. So here we look at, in the same approach of the 7 clusters of the 7 people, and similar to the 2-plane, we look at those projections plus the PCA, just because it's commonly used, and want to look at how those views related to each other. Can I understand better how the overall picture is built? And again, you want to think of this as a very coarse sampling of your Grassmannian. Later on, we want to think about how do I do that more automatically. So here, for example, you look at the data set, here selecting the PCA view. Typically, you get the data spread a lot. The colors are actually the clusters, and so here each point corresponds to a particular picture. You can navigate, but it's very hard to make any sense out of the cluster. In fact, actually, this corresponds to the lighting condition. The PCA clearly favors spreading things so that you have this circular model, and around it you have the different lighting condition. But now I can rotate from one view to the other, and you can see that depending on the view, some of the cluster emerge more explicitly, exactly because here you see the yellow, it's on the top left, and so on. So different views separate different data set more or less effectively. And overall, you start getting a picture of how those clusters related to each other. When they converge, there is a place basically where all the clusters on the top right tend to converge, and different views that help. So here, for example, we follow the yellow cluster. In fact, it's one of the persons, but at the top, when the lighting condition gets dark, it merges with the others. Notice that, so one is the ground truth labeling, the other is the automatic clustering, and it can help us, even if we are in relatively high dimension, to understand how well the clustering is behaving. Do we have to change the algorithm and so on? And what is the area of misclassification, and understand why that happens. And here we can look at the fact that dark picture kind of makes sense, are harder to distinguish. So people that do it manually kind of take advantage of additional information. And so this is one way of looking at the data. And here, so you see the distribution of the points correspond to the rotation of the lighting condition within the same cluster. In general, here you kind of start thinking of sampling the space in terms of space of views into the data. Now, if we want to do this more automatically, how can we start thinking of scoring somehow a good view from a bad view? So in general, you want to think about my Grassmannian, say if I were doing 1D, it's my circle. Now I want to have a function on that circle, and here that's what we can borrow from those various metrics that were used from scatter plots. I have my set of points. I have the domain where, in some sense, I have all possible scatter plots, not just the ones with particular coordinate systems. And I wanna look at the plots kind of as a function distributed on that domain. And now, how do I pick good views out of this domain? This is actually a general ranking problem, right? Even when you do search on Google, is it ideal to represent a population to just have the top 3 ranks, for example? And this came up a lot in literature about kind of cultural bias about things you find. If you just pick things out of ranking, you end up clustering your choices around the same global extremum because they're all high values. But for something like views where you expect some kind of smooth change over the space, that's probably not a good idea. What you want to do is go back to your topological analysis, and each of those more cells are probably representing a group of views, hopefully the metric is good, that are similar or good. And out of that region, I might just pick the maximum, and then I might pick the second maximum instead of one more view within the same more cell in that space. And so this tends to give a kind of a good sampling of the space. So you now go from just sampling your high-dimensional space to sampling somehow the Grassmannian. You might want to build your neighborhood graph or kind of whatever is your favorite algorithm for trying and get some connectivity. Now, for each of those are views, you can just go draw them and build a quality metric. So you can think of now you have a function on that domain. And now the question is, can I show that function in a very simple way so that I can use it as a tool for navigation? And that's where now we look at building something like the topological spine, so that topology tree, I can just flat them on the screen and turn that into a component in my visualization environment to let me explore interesting views in the data. So this would be now the composition of the Grassmannian, and then I can just take the graph of the maxima if high value are interesting, if the metric tells me high value. And so that could become my user interface component that it's coming from topology, but I don't need to show that in the even higher dimensional space itself. So for the metrics, obviously now, given the topology, we can think of the persistence diagram of each of those, and now my spine could be full resolution or simplified, depending on how complex I want to make my navigation space and how detailed I want to make things. And of course, often in a plateau in the persistent diagram, it's kind of a good sign that you have an interesting condition, but obviously that's not guaranteed in any way. And so we can look at different metrics with different persistent diagram and see what consistently may or may not happen. So those are, for example, the persistent diagram for different metrics. From the clumpy, stress, it's always very similar, sparse, and those are different data sets. And you can get a sense, this is more in terms of heuristic, of which of those metrics may lead to more differentiation in the way you look at the data. So if you take a data set entirely new, this is something we tried for this type of work on word embedding, so taking words and representing them with statistics on the relationship with the other words. So you have an array of words, and then you have a scoring with a high-dimensional array. And so this is a particular data set taken from a subset of Google News words. And then here we look at simplifying the representation. And now on the left, you have a very coarse view of the topology of, so here we're selecting a particular metric. We can choose the persistence, and then we have the topology on the Grassmannian. And on the right now, when we select a particular viewpoint, you see the viewpoint in the high-dimensional space itself that changes, and let us explore the data, and that highlights different way of clustering of different nouns, words of different types, and you can start getting an impression of how they are related to each other, right? So some views show them overlapping, some show how they're well separated. And so you go beyond the just numbers of a clustering algorithm, you get an intuition on how things work together. So here would be the view you get out of the global maximum. Some words are kind of separated, some are, so here you have just grouped together country, city, all the other are together, but there is no good clustering there. So if we pick these other local maximum, we have a better separation still on one side countries and city, but then within the other group you have adjective, nouns, so one type, and one nouns of the family on the other type. And again, different views show structure in the data in a different way. And so the question is, this just to, as a concluding example, also to be very honest and systematic, is that some of the stuff seems to work very well. It's not always like that. The initial remark of fooling yourself is actually very important. You want to look at those high-dimensional spaces are always undersampled. And I know it seems a blanket statement, but the reality is if there is any interesting stuff, any uniform sampling or reasonably good sampling would be crazy expensive. And so, and we have the problem that we don't have the experience to go in that space. So in a way, it's important to remain grounded in a very rigorous process of we draw conclusion, we make hypotheses, and then try actually to prove them wrong, and not just try to do the looks exactly how we expected. That's a way you fool yourself. So here, for example, in this word embedding problem, there is this classical conjecture in the natural language processing community that there is this notion of analogy. If I have vectors on a certain dimension, let me go from a man to a woman, from a king to a queen. Those are all directions, they have the same direction that made me go from a job in a male condition job to female condition, and they conjecture those lead to those set of parallel vectors. The question is that true? To what degree, right? Because you build the embedding yourself, so it's kind of, there is a vicious cycle of expectation and looking at the results. So here we look at, again, it's a high-dimensional problem. You have a set of points. If you think about the direction from the left to the right to be the analogy, then you can kind of, with some techniques like SVN, you could build the plane that separates your clusters. And now you can think about, okay, I have those are a bundle of vectors. I could look at the vectors on the side so that I hope to make them look parallel to each other. And I can look at them directly in front. So each vector should become a point because I'm just looking straight down to the direction of the analogy. So that would be if it's true that I have those vectors, I should have those views. And the question is that true or not? So here, but immediately you have the question is, well, if I look at them from the side, which should I align and make those groups kind of vertical line with each other, or should I really make the vectors, even if the cluster kind of overlap, but the lines are more parallel to each other? You have, again, this high-dimensional spaces, lots of interesting choices. And so here you start looking at, if I look at my projections on a PCA, obviously it does not show directly there. For some vectors it does a good job, for some are very short. If I actually look at the SVM hyperplane and one of the dimension of the PCA, I naturally get the words more or less, the pair of words more or less parallel to each other. How this leads to something really true. Here would be the view on the left is kind of my side view, and here on the right is the front view. Is this a confirmation that the hypothesis? Now the question is, if it's true, yeah, you can see actually interesting outliers and ways you might correct your representation. But again, you want to verify, I mean, it's high dimension, so we don't know how a bad example will look like. So if I show you those 4 ways of building those word embeddings, and those are my side view. Would you think of those kind of being a good indicator that are parallel to each other? And for example, our impression was, yeah, they look all, so it seems to confirm all of them, right? So those are 4 different ways. One is called word-to-vec, one is normalized, and so on. But I don't know if anybody would spot a bad one, but those are so 3 are computed with 3 different techniques. One is actually a random data set. So when you're looking at data in high dimension, you have this problem. It's a more general problem when you deal with big data. If you really look for something, you're very likely to find it because the space is so complex. So you really need some guidance in the interpretation of the visualization you look at, so you make that you don't have kind of misleading information. This is another way of looking at 2 possible side views of a data set. The problem is both of those data sets are random set of points. So I'm kind of fooling myself. So how do I give a guidance and a legend to understand that? So what we did is actually start looking at random data sets as a way to compare and measure how meaningful the visualization is. So for each of those views, on the top, we're actually looking at, in this case, the distribution of the angles of those vectors. And now, so for a meaningful data sets like the one on the right, the triangle there marks the mean of the distribution that is actually being displayed compared to the histogram of the random data. That's way on the left, is way lower. And so that's actually very different from a random distribution. The one on the left, you see that the mean is actually equal or higher than the random distribution. It means that that way of looking at the data could happen just out of the random data set. So if I think of that, oh, nicely spreading my 2 clusters, I'm fooling myself. That could be the result of a totally random data set. And so to complement the visualization with some auxiliary information that start building trust, avoid some of the uncertainty that comes from the data, if I go back to my hypothesis in my view, I always associate them with those histograms that are on the top. And so those are particular 2 views that are confirming the hypothesis of the analogies, and they're actually shown to be really different. For that viewpoint, you wouldn't be able to easily reproduce that type of view with a random data set. So just to conclude, kind of visualizing data set, it's obviously fun and very difficult, and there is a lot of work that needs to be done. Obviously, in terms of computational challenges, data tends to be big really, really quickly, especially if you want to have a decent sampling. Lots of the other talks were going down that road. There is a question really how you visualize it and build, help people build mental models that make them understand what's in the data, and how you integrate the analysis so that you can build those models, ask precise questions, but then verify and maybe trying to disprove whether your hypothesis is correct or not. And thank you very much for your attention.